Hello, everyone. My name is Eliezer Souza da Silva. I'm a PhD candidate at the Department of Computer Science, supervised by Helge Langset and Harry Ramanpiaro. This thesis is titled Factorization Models with Relational and Contextual Information, with a subtitle Predictive Factorization, Point Processes, and Neural Sequential Models. Thank you for coming for this presentation. The outline of the presentation will include an introduction where we'll talk about our goals, motivation, and research questions, and methods and tools that we use during this thesis. We'll also then include our contributions, including Poisson factorization models, time modeling with point processes, prior specification, and hierarchical models, and conclude with some remarks and future directions of research. The main reason here for us to start looking into context is this situation that we encounter, all of us, in this world of a lot of interconnections, multiple networks, multiple opportunities to connect and consume items and in different contexts. So this generates a challenge, which is about how much information we can consume or how much information we can attend to at once. And this example here of a figure shows this network of multiple connections representing this world that we live now. So this information overload creates the challenge of filtering relevant information to increase the user utility or the value of the system for the user. This is basically the idea that there is a certain amount of information that you can consume, and there is a certain value for different sources of information. So a system should be able to assist you by creating adaptive interfaces and by learning your information needs based on your interactions and behavior with the system. So that's overall our goal here. And this is a goal not only for this thesis, but for a large subfield of information retrieval, recommender systems, and adaptive interfaces in computer science. There is also associated risks and opportunities here with recommender systems. There's a lot of discussion about phenomena such as filter bubbles or ideological echo chambers, which is the situation basically that a system starts to generate and recommend content only from a certain context or a subset of content that might trap the user within that context. So we want to understand better, we want to include different contexts, and this is a big motivation as well for that. The basic setup here that we start with is this setup where we have a certain amount of users and a certain amount of items. So user 1, 2, 3, item 1, 2, 3, 4, and the users, they interact only with a subset of the items. So no user is interacting with all of the items because the list is too big. And based on this bipartite directed graph of observation between these relations, we want to take that into account and predict and rank new connections. So try to say, maybe user 1 will like to see or consume, observe item 2, for example. In that basic setup, we want to extend with the idea of contexts. So context here is, for example, time, location, social network, content, different basically sources of relations and information that can modulate basically how the user will interact with a given item. So the information need of the user fundamentally is not static. It changes, and it changes with context. So that's what we want to account for here. And a fundamental idea here is that we can use context to give us auxiliary relationships between user, items, and other entities. And we use and we model these auxiliary relationships in our models. So context, why we want to take that into account. So one thing we mentioned already is this ability to capture nuance and about the user preference. So the user preference is not anymore static, but it has some change to it, some dynamics that are important. And we want as well to go from take into account only the user item matrix or graph to take into account many other sources of information. So by doing so, we hope to achieve a model or a system that is able to modulate its ranking and achieve higher granularity with respect to what is the information need of the user at a given time or a given other context that we want to take into account. So overall here, we can organize these goals in this following way. We have the overall goal of designing models with contextual information, and we decompose these goals in two sub-goals. One is a goal of designing models for different tasks, basically. So here we enumerate certain contexts that we will highlight here: content analysis, social network, timing, periodicity, session-based, and sequential information. And in this subtask also, we focus on a posteriori predictive evaluation. As a different subtask to the initial task of designing models, we want also to obtain methods to do a priori analysis of the model. So as we notice here, this first approach, it's basically an approach where you design and test models on a given data set. In this second approach, we want to be able to tell certain properties of the model a priori before fitting the model on any data, for example. And one sub-goal here would be, for example, to be able to tell something about hyperparameters, specify certain values or a range of values for them. Related to those goals, we have research questions. Research question 1 and research question 2 is about including user social network and item content and including periodic time context. So how do we do that? What advantage we gain from doing that? Research question 4, it's all about including temporal information in sequential models. So we'll discuss all of these in details, but those and together with including implicit feedback, these are in this first big sub-goal of designing models for different tasks. And then as for the second sub-goal, we have the idea of exploring hyperparameters prior specification. So this a priori model analysis. So how would we do that? What sort of things we can say about it? In the thesis, we go in more details about the research questions, but here we just highlight them with connection to the goals of the thesis. The main methods and tools that we are going to use is Bayesian modeling, latent factor models, prior predictive checks, and count models and Poisson factorization. We'll go now into explaining each of them. Bayesian modeling. Contextual relations introduce in our design or in our tasks the possibility of uncertainty and ambiguity. This is a challenge, but also we know from Bayesian modeling that there is a way to basically take that into account. So Bayesian modeling gives us a language to reason logically and statistically about relationship between the variables. So we take all the variables that we consider as important, both observation variables and parameter variables about our models, and we can reason, we can say how they are connected and incorporate prior knowledge and also do statistical analysis on it. This means that our design space here consists of choices regarding an independent structure of the model. So basically how those different variables, both parameter variables or observation variables, are related, and distributional assumptions. So as we show here in this diagram, which is a very high-level description of a Bayesian model, we have a distribution for the parameters theta of a model. We have a conditional distribution, which the distribution of the parameter theta is called the prior distribution. We have this conditional distribution of the data given the parameters, which is usually called the likelihood. And we have the data here generated from this model. So we have our model here defined by a prior and likelihood. And we have, as a consequence, a data generating process here. These tools allows us to talk and reason mathematically and computationally about the structure of the model, but also it allows us to go from the data generating point of view, where basically we tell how our model assumptions leads to the sampling or generation of the data, but also to reverse this process and, given a data set, be able to tell, for example, what is the distribution of our parameters. So this is by applying the Bayesian rule or Bayes theorem. The latent factor models is a rich set of models with a long history in multiple fields, both in theoretical and applied statistics, computer science, where the basic idea is to embed a set of entities in the same latent space. And by doing so, we can now use basically linear algebra to reason about the relationship between those entities. So here, for example, we could have a data matrix that consists of words and documents, and we would, for example, factorize this data matrix, counts of the words and documents, and by factorizing this matrix, we'll be obtaining embedding. So each word or each document in this data set would have now a representation as a vector in this latent space. There's many techniques that can be used and use this idea. So from basic pure mathematical techniques such as SVD, or techniques such latent semantic indexing, latent directional allocation, word embeddings, and collaborative filtering with matrix factorization, recommended system context. Here now, we talked about basically two modeling tools, but also we want to talk about the model design cycle. So we have this challenge of iteratively designing models. So we have different assumptions. We go from those assumptions about the data and about the problem into certain choices of how the model is going to be, how the variables in the models relate to each other. And this is an iterative process because we make those choices, we train in a given data set, we evaluate. Also, there are basically two approaches here to check our model. Prior predictive checks and posterior predictive checks. We want to explore those two approaches. Posterior predictive evaluations are more typical, where basically you train your model and you evaluate on a test data set of your model. But we also want to explore the idea of prior predictive checks. With prior predictive checks, the idea is that we have a hierarchical model. So for example, in this diagram here, we have a hyperparameter lambda. This hyperparameter lambda defines a prior distribution for our latent variable z. Our latent variable z it can be conditioned on, and we will generate our observations x. But also we can marginalize the latent variable z, meaning we can look at our model when we explore different possible values for the latent variable z. And by exploring all those or multiple of those values, we can find a direct connection or a direct relationship between the hyperparameters and the observation. So the prior predictive distribution is this distribution that we obtain by marginalizing or basically integrating or varying over all the possible values of z. And it's also a useful both theoretical and computational tool for us to analyze the behavior of our model with respect to how the hyperparameter is related to properties of the observations. So we'll use this also as an analysis tool, a priori analysis tool. Going forward, we want also to take into account the difference between implicit and explicit feedback. Many of those models in the literature, they use only explicit feedback, meaning that the user will tell to the system a specific rating regarding how they feel about a given item. So for example, user like or don't like, or like with a rating 5 a given item. But the great majority of the data sources, we have actually user interaction counts. So how many times a user visits a page, how many times you listen to a given sound, how many minutes we spend in a page. So there's a lot of interaction count data, and this is what we call implicit feedback, because this is not a direct rating of, say, how much you like a given item, but it's a proxy and indication of implicit preferences with regard to those items. So we want to create models and use models that take that into account. And for that regard, there is a family of models called the Poisson factorization models. Those models, they are designed to take into account these implicit counts. So these are count-based models, and they were created in, mostly started coming up in 2014, and outperforming the equivalent Gaussian-based factorization models in benchmark recommendation datasets. The basic construction here is represented by this plate diagram, and here we have also the representation in terms of equations. So we have a theta u, so it's a latent factor for the user, a beta I for the item, and they interact via sum to generate the rate, which is the parameter of the Poisson here. So the rate will depend on user and item, and for different user and item, we have different rates defined by these latent factors of the user and the items. There's a nice property of Poisson distribution, which is additivity and decomposition of the rate. So this is represented here, that meaning that we can sum rates, and this leads to summing the counts. And also, if we can decompose the counts into sums, this means that we can decompose the rates into sums of the same amount of components. This will prove important both for computational properties, but also in terms of sparsity of the observation and the different sources of information that we want to integrate. So now we want to discuss some of the contributions of this thesis. We'll talk about Poisson factorization, time modeling use in point process, and prior specification in hierarchical models. Content and social network joint modeling. So this is the first first list of contexts that we said that we want to take into account, and we want to joint model them. So joint modeling of content and social network. One of the reasons here for social network is the phenomenon of homophilia, meaning that similar people like similar things. This is a phenomenon that happens in social network. And beyond that phenomenon also, we know, or we can intuit, that the item exposure is also positively influenced by the peers. This means that even if you don't like the same things as the people in your social network liked, the way that you'll be exposed to items is going to be mediated by your social network. So item exposure is influenced by the peers here. So those two observations are important and lead us to think more about how to include social networks in our models. Item content analysis here is about basically topic models. So we want to take into account the distribution of words or descriptions in each of the item, and we can use that to deal with the idea or the problem of cold start items. So items that have no user interaction data. Nevertheless, they have a description. They have words describing them, and these can be used to generate recommendations, because now we can interconnect different items based on the topics or based on the descriptions of them. So we can intuit that many preferences can be influenced by those topics. So certain users might be more interested in a given topic rather than others. So this distribution of topics should be informative as well about the user preferences. So we want to model this jointly, and we want to include that in a Poisson factorization model so that we also gain this count observations type. So here we represent this scenario where we extend our original just user item connections with now social network and topics as well. And we represent here the model that we obtain by doing so as a factorization model. So here we have word, so item and word, so description, so a data matrix of distribution of counts of word counts for a given item, and also a data matrix of user item interactions. We observe those, but also we observe the connections between the users. So how the user are interconnected with each other, and we want to use those interconnections to influence and to basically constrain how the user topics is going to be created. So the user topics, the item topics, and the topic word topics, those are the latent factors, and those now are going to be constrained by the social network and by the observations both of the user item interactions, but also the word item interactions. This work led to a publication, content-based social recommendation with Poisson matrix factorization at ACML PKDD 2017. The final ranking here that we obtain is going to be the combination of all those factors. So we have the user preferences, share item topic intensities, and item topic offset, and summing now with a weighted sum of the social network contributions for each neighbor of the user. So the reasoning that this also works very well is because of the additive property of the Poisson, meaning that any part of this sum and this weighted sum that is not contributing, or basically we can think about latent counts related to each of those subcomponents here. Results here, we show just briefly some of the results obtained in this work. One is comparing Poisson matrix factorization with content and social networks with equivalent Gaussian-based models. So we have the collaborative topic regression with social and matrix factorization, collaborative regression, and probabilistic matrix factorization. All these are Gaussian-based. So there's a clear advantage here of using Poisson and also Poisson matrix factorization with content and social networks. But also we have here a comparison between multiple Poisson models. So basically turning off either the social part or the content part or both of them. And there's also a gain from considering jointly all of those relations. Also, we show here a small experiment that showed that this model is very economical in a way, because it managed to get the best results with very few latent factors. Basically 15 to 20 factors gets the best predictive performance. Next on that, we explore the idea of periodic time-aware Poisson factorization. So here we have a task which is indoor recommendation task. We have a location. So this is an indoor shopping mall with different access points representing possible locations that the user can go. And we have traces basically on time saying that the user was in this access point at this time, and so on and so forth. So we have information about time and we have information about space. But also because this is a public space, we want to take into account not only not people that comes just one time or two, but periodic behavior. So either collective periodic behavior or individual periodic behavior here from the users. The challenge of integrating this periodic type information is related to the challenge of creating chains of latent variables that are interconnected in time and has this, I would say, like this cyclical interdependence. The way we did that is by creating an auxiliary variable observation here, represented by S. This is just a dummy variable that we set to a fixed value, say 1. And by doing so, we create basically a prior that each time stamp, basically is consecutive time stamps, they will have the tendency to have the similar values. And finally, we have this interconnection between the beginning and the end of the chain, also creating this tendency to have the same values on the beginning and the end, meaning, for example, if you go from Sunday to Monday and Saturday, Sunday again, all of those factors for all those days, they will be interconnected in this cycle. Here we extend again the basic Poisson factorization model and include now time dimension. So it becomes basically a tensor factorization and time dimension with these cyclical chains. We made two versions of this model, one without auxiliary, one simple model with only the time chains, and the other with an auxiliary data matrix here connecting, for example, the access points with different categories. We show here just a sample of the results tested on a simple baseline compared with SVD and SVD++, which takes into account time, and we can see positive increase in performance. Next, we want to talk about temporal point processes and how we can extend this idea of time context, but also sequential context of items. So, as we talked before, the Poisson model is a count model, but in the Poisson model, there's a rate, and this rate is constant. There are ways to deal with that. For example, here we created multiple rates in different timestamps, but this is basically similar to creating a grid, but it's fixed, so a static grid of timestamps. And this is not sufficient for more dynamic situations. So in this case, there are a different family of models that's called count point process or temporal point processes, which basically extend these Poisson models with this idea of a history of events and of an intensity function that will basically have, it's basically as if you had a variable rate that depends on past events on these processes. So here is one example of a Hawkes process. You have one view of these, which is basically the counts of number of events that is happening. So we have like 2 events around 20 and so on and so forth. But also you have here this conditional intensity function, which is HT, represent this history of events at a given time t. So this conditional intensity here is now changing over time, and it changes both depending on the number of events. So once one event happened in the history, it increases the chance of a new event happening, and there's a exponential decay here. So we want to take that into the context of session-based recommendation and more even the multi-session recommendation. So in this problem, we have now a sequence of sessions. So each session consists of the user starting to observe or interact with certain items. Now we take into account the sequence of item interaction. So before we just took into account if there was an interaction or not, or how many times there was an interaction. Here we want to take into account the sequential nature of this interaction, both at the local level of the session and at the multi-session, so between different sessions. And then we extend this model with the ability to also perform time prediction by coupling here a next prediction of the next session, basically. For the sequential, both intra-session and inter-session, we use a recurrent neural network. And for the time prediction, we have a temporal point process model. So here is the resulting schema for this model. This is resulting in a publication paper called Timings of Essence, a joint hierarchical RNN and point process model for timing item prediction, done in collaboration with Bjorn Vassoy, Massimiliano Rocco, and Arlen One, published at Wisdom 2019. And basically is this idea of combining recurrent neural network for intrasession and intersession, and in the intersession level, using the basically the state of the recurrent neural network as a latent representation that has encoded the history of events, and we use that latent representation in our time model. So now we have this temporal time model So here we represent the equation for the log likelihood of this model. This symbol here means that we are taking into account the history of events. Lambda here again is this conditional intensity function. We won't go much into detail here on the math here, but this can be combined with the neural network, basically by giving a form for this function that it's defined by a neural network. And in this neural network, this is shared representation with the recurrent neural network, where we obtain our embeddings of the past sequences of items that was interacted with. And also we observed by looking at the gradient of the log likelihood that this particular construction had both a linear term, depending on basically a linear term, and also a more complicated nonlinear term. And the conclusion from analyzing this is that these two terms, they are related to short-term and long-term predictions. And from that observation, we created also a modulation in the loss function in order to focus either in short-term or long-term predictions. Here we show just a sample of the results. There's more results in the paper in the thesis. Here, basically, we show different values for this alpha factor, which is the factor that we use to modulate between short and long-term predictions, and comparing it with different Hawkes models. So Hawkes model is the model focused on only time prediction here. So this is the mean average error of the time prediction. And we show that we can get models that modulate either for short-term or long-term predictions, for example, this one here. And in this figure here, we show this modulation more clearly. So basically varying this alpha from 1 to 0.3, we can modulate between focus on long-term or short-term. Now we want to talk about the idea of prior predictive matching. So as we talked before, those three models that we designed before, they are focused on different tasks, different contexts, different model design. So for each task, we design a different model. Now at this part here, and we evaluate these in terms of predictive power, posterior predictive after training. Here we want to look at a different angle about basically how we can analyze this model a priori. And as we discussed before, there's this prior predictive distribution that we can use. And also together with the prior predictive distribution, we had this idea that we can basically sample multiple points of the latent space. And by doing so, we are marginalizing the latent variables. And one way to think about it is that we are simulating data from our models before we fit the model with any real data. We are just simulating data from the model given certain hyperparameters, and we can create basically virtual statistics of this data generated from the model. And from those virtual statistics, we can see how varying different hyperparameters, the different statistics, or basically the different data generated by the model, they change. So this is the idea of prior predictive matching, that there's different, if we vary hyperparameters, we obtain different virtual statistics of our models. And these summary statistics, we can do moment matching there. And this can be a source of intuition about basically how the hyperparameters are affecting properties of the models, for example, in terms of moments, or mean or variance or covariance or other summary statistics. But here we focus mostly on mean, variance, and covariance and correlation. We do apply this on hierarchical models, and we apply this in particular to Poisson models. So here, by applying this idea and using the techniques or the results from law of total expectation and total variance applied in Poisson factorization, we could obtain analytical solutions here. So for example, obtaining the dimensionality of the latent space. So what's happening here is that we took this idea of prior predictive distribution, meaning that we have our model, we try in to generate basically data from our model. In this case, purely theoretical, and we analyze how this data what is the properties of this data from the model. So virtual statistics. So in this case here, the variance or the expected value or the covariance here, those are virtual because they are assuming that the model is generating data. And by doing so, we doing certain amount of algebra, we obtain closed form equations for example, for the number of latent, for the dimensionality of the latent space, which is a goal that has been missing in a lot of the existing models, but we did obtain here in this case. But with this caveat that this is assuming that we have data that is generated from the model. If we assume that the real data that we have is matching the data from the model assumptions match the data that we have, we could also calculate this statistics from a real world data set, but this is just an assumption basically. So also by doing so, we can calculate other hyperparameters. We can calculate if we consider that we have a gamma with hyperparameters N, A, and B that control the mean and variance, and C and D the mean or the variance of the items. We can calculate basically hyperparameter A and C, and we can find a relation between B and D. All of this is obtained here in this paper and discussed in details. This is available on arXiv, and it's on submission right now, collaboration with Tomasz Kozmich, Marcelo Hartmann, and Artur Flame. And here we can see that a problem that initially consisted of, say, 5 dimensions in terms of hyperparameters is reduced basically to 1. Also, from this line of reasoning, we developed a general algorithm. So here the idea is that, again, you can sample from the model, generate virtual statistics, calculate, for example, summary data, and then we want to optimize or basically take gradients from these samples or from this summary data. And by taking those gradients, we can basically do moment matching based on gradient descent. So here we do a representation of how this gradient propagation on top of the expected values can happen. This depends basically on all those parameters being reparameterizable. So we deploy here the reparameterization tricks available. And by doing so, we are able to have a generic algorithm for any case. So as a sample of also results, we show how the prediction for the latent dimensionality matches. So the equation here is a simulation of multiple matrices generated from the model, and what is the dimensionality? So multiple dimensionalities assigned to it, and if we can recover it by calculating this equation. And also in the second figure here, we show model misspecification. So here we do, instead of using Poisson, we use a negative binomial, and also we use random, basically zeroing certain entries of the matrix. And it's not perfect, for example, in this case of random zeroing of the matrix, at some point the performance drops very high. But even here, in the case of a negative binomial, it performs reasonably okay to a certain degree. Again, this is to show that we have certain tools here, but they assume that small model misspecification, and with higher amount of model misspecification, we would need to adjust those equations. So concluding remarks here, we have highlighted this in this work, the need for including contextual information in recommender system, and in particular in a Poisson recommendation setting. We showed different model designs for different tasks, basically networks, textual content, topic analysis, time domain, sequential information. And we also developed some tools for a priori checks of model design. These two these are the sub goals that we defined in the beginning, and they allowed us to explore the research questions also about what are the different advantages and limitations of these techniques. As future directions, we can see the possibility of extending these joint matrix and tensor factorization ideas to generic families. There's been a growing body of research into creating, say, tensor networks or tensor matrix networks, and we see that there's a natural extension here from these ideas to those types of ideas. In terms of the temporal and session-based models, we see the possibility of using attention models or other forms also of models that try to capture long, short dependencies from the data, because in this case, we had a hard-coded control for a long, short-term dependency in temporal dimension, but maybe this can be done from, say, end-to-end, and from the idea of Bayesian workflow, which is an idea that's been developed as well to formalize this design cycle of many Bayesian models. We see the prior predictive analysis of more complex family of model as an interesting direction to pursue, and as a nice contribution or important contribution, creating more tools for faster and a priori analysis of the models. So these are this is the work that we did in this thesis. Thank you very much for taking your time and following this presentation, and open to any questions that you have. Thank you very much.